Like, what did we end up with? Like, what was the form with just the plugged in values? Yeah, so what was it, Callum? So 8 equals. Okay. Wow, Jason, you have such great foresight. Anyways, we are going to put that in a matrix. What? That's crazy. Could you believe it? So, I'm going to go through this because we're going to teach you something called upper triangular form, which I'm guessing some of you might already know. So, yeah, Jason, excited about this. So, we're going to put this in a matrix. And so, here's the thing about upper triangular form. So, usually what we did earlier, where we solved for doing the reduced row echelon form to solve for our values in a systems of equations. I'll just kind of verbally explain it to you guys. You don't have to write this down. But when we solve for it, when we did this, and then we got like a values over here, we were able to easily find x and y, right? But we can actually take a little shortcut here. We don't necessarily need to solve for that value there. Let's say it's just a random value, like 1/8. We can keep that there and just kind of reduce all the values under the diagonal and including those ones, because what this actually does is it makes it even easier to just use a regular systems of equations to solve it, because this will just end up being, this turns into what? Y equals 4. If this was like an x and y system of equations, and this would be x plus 1/8 y equals 3. And why the upper triangular form is easy is because you can just take this y and then plug it into the equation up here to easily get the x. You don't really have to even like solve the systems of equations. You just continue. So if you have like, let's say you have like a 4x4 matrix, do you really want to reduce all rows of that down to reduced row echelon form? Probably not. It's going to take a long time and it's a little tedious. What you can do is find upper triangular form. See, it's like, wow, it's a triangle. That's crazy. And you can just start from the bottom and find your one value and then continually plug it back in up towards the top. If that process, does that make sense? Does anybody have any questions about that? No? Okay. Cool. So what we're going to do over here, would you guys want to attempt this on your own first or go through it? You just go through it? Okay. We're going to go through it. So let's set up the matrix. Would anybody like to set up the matrix for me? I'm going to grab Miss Edie of the cards.
Yes.
Okay. Enzo's not here. Jason, congrats. Do you want to set up the matrix, the augmented matrix for me?
Yeah, sure. Open matrix project 3 and 1. And about 2, 3. The augmenting line and 8, 0.
Nice job. All right. Cool. So, does anybody have any suggestions for, let's start with this value here, make that a 1. Anybody got any ideas of what we can do? Oh, yes, we can do that. We can do 1/3 times row 1. That's going to result in 1, 1/3, 8 over 3, 2, 3, 0. Nice job. Okay, now what else can we do? Any ideas?
Subtract 2 times row 1 from row 2.
Yeah, so we can do -2 times row 1 plus row 2. This gets 0, 1. And this ends up, what? Oh, oh wait, I'm doing this different, sorry. 0, I skipped ahead a step. 7/3. Yeah, I skipped ahead. Wow, that's crazy. And now what do we need to do to finally turn that into a 1? Suggestions? Nice job, Callum. You're killing it. You're just a matrix demon. third,
Algebra.
third, and then 0. What? Okay. Negative 48 over 21. Trust me on the math. So guys, Jason, you have a question? Okay, awesome. So, okay, yes, but this is for proof of concept because there's going to be bigger matrices that are going to be like 3 by 3s, and you'll want to do it. It's okay, just trust me on this one. Okay. Yeah, we'll reduce the fraction. Okay. Okay. Sorry, Callum. Okay, sorry. I did it in a later step. Sorry, Callum. Okay. My bad. Okay. So, now, remember? Sorry, Heather. I apologize. C1, C2, C1, C2. So, what does that mean C2 is equal to? You're so studious, Mina. All right, and then what is the equation up here that this will produce with our C values? Yes. And look at that. Isn't that crazy that we can just plug that C2 into here and easily get our C1 value? So does that make sense to everybody why we would do this instead of solving for reduced row echelon form? Yes. Okay, awesome. So, does anybody want to do the math? Do you want to do the math, or do you want me to? Well, I'll give you the numbers. Nice job, Mina. You're so good at math. She solved for it, obviously.
She did some fractions.
16 over. Oh wait, that's 21. Not 7. You know, she knew. All right. Here, and then, am I?
16 over 21.
Oh, you're so right. I don't need the. It's my bad, guys. I already multiplied that in. Thanks, Jesse. And then, okay, C1. No, it's okay, Jesse. And then C1. Do we want to do the math, or do we? Okay, let's just skip to it. C1 is 20 over 7. Wow, great job, guys. We found our C2 and our C1. Now let's put it all together back into the original equation. Just anybody, and here's the thing, when you re-represent it back in your original equation, if you remember that we had the big x sub 1 is equal to, what is it? It was 3e2t and 2e2t. You don't have to write all that out because in the answer key, it's just going to have it as x1. That's all it's going to be as. So, you don't have to do that. So, would anybody like to write out the final equation? Jason.
x1 of t.
Or you don't have to write out the two different ones. We're going to combine it back into one equation. Because because remember yes, Emilio. You remember the superposition theorem when we constructed it as one equation originally? You might have it in your notes. I didn't write it up here. And then we divided it into two different, well, not actually divided, but we separated it into two different equations using, it's called scalar form. Do you want to, what is it? Do you remember what the original equation was? Maybe?
I think so, yeah. So that one equals, xt equals
Nice job.
4 over 7, 2 by 1 matrix.
You don't have to write that matrix. You can just go x sub 1.
Oh,
Yeah.
that's convenient. Okay, then plus C2, 8 over 3. Negative 16 over 7.
Yes. Nice job. Okay, guys. That's it. I think,
X was.
yes, vector hats. You're so right. I don't think that one does because that's a capital. Okay. Okay, so that is how you solve initial value problems for matrices. Okay, guys. Okay. The next section of this lesson talks about linear independence. And basically what I've written up here tells us that when finding if something is linearly independent or dependent, which we will find the method to solve for, but what it means is that the vector valued functions x hat sub 1, x hat sub 2, all the way to x hat sub n are linearly dependent on the interval I, provided that there are constants c1, c2, all the way up to cn that are not all 0, such that when our solutions are added together, it can equal 0. It'll equal to the 0 matrix. If not, then the functions are linearly independent. And how we determine this is the Wronskian, which we discussed earlier. The Wronskian for first order linear systems. So I should probably have a little bit of so anyway, so we're talking about the Wronskian. So this Wronskian tells us whether or not basically the given solutions of the homogeneous equation are linearly independent, which you can kind of make a note of that if you want to, but just know that this Wronskian kind of tells us if something is linearly independent or dependent. So if we are given the solutions, so just like I had earlier, let's say these are our solutions and they're going to be represented in this matrix. Go x sub 2, 1 of t, x sub n, 1 of t. Our column matrix, so that's one solution. We'll have another one here. Oh wait, no. X sub 1 of t, x sub 2, 2. All the way up to x sub n. So these are our solution matrices, and we set them up in our Wronskian, which is represented with a W. The reason why I have these certain subscripts is because they're going to line up to our determinant terms, and our Wronskian would be x sub 1, 1 of t, x sub 2, 1 of t. This could go all the way down to as many rows as possible. X sub n1 of t. In the next column, x sub 1, 2, x sub 2, 2 of t, down to x sub n2 of t. Let's go as many columns as we want. X sub, I'll go over here. I hope this is visible. Maybe it is. Oh boy. Well, I'll kind of explain what each term is as I go through it. X sub 1 sub n of t to x sub 2 n of t down to x sub n of t. So this Wronskian, which we kind of discussed how to solve for earlier, what you do is you take the solutions that you're given, and you might solve for them later on in this process, or for at least this section, they're going to be given to you, and you can set them up in a Wronskian. So as you can kind of see, hopefully maybe with, I don't know if you can see with the glare, but we've got there can be as many terms as we wanted. So there's x sub 1, 1 of t, x sub 1, 2 of t, x sub 1, n of t, so that's however many columns you want, and then all the way down, you go x sub n, 1 of t. So however large your Wronskian is, you set it up to the determinant and solve for it. Excuse me. And we'll do an example here pretty quick. Okay, I turned the lights off, so hopefully the glare is maybe a little bit better, but we'll see. So now we are going to try to use the Wronskian that we just learned to determine the linear independence or dependence of this system of differential equations. So here's our two given solutions. The column vector 3e to the power of 2t, and then over 2e to the power of 2t, and then the second one is e to the power of negative 3t, and then 3e to the power of negative 5t. So what we pretty much do, which we were shown just after, is that we set this up, and I'm trying to make sure we can see. Set this up in a Wronskian, so 3e to the 2t, 2e to the 2t, 3e to the negative t, 3e to the negative 5t. Okay, and then this is just going to equal, we just do our cross multiplication here to find our determinant. So that's 3e to 2t times 3e to the negative 5t minus 2e to the 2t times e to the negative 3t. And now if we look at this, this ends up being 9e to the negative 3t minus 2e to the negative 3t. And this is not equal 0. So we know that they are linearly independent. So those two solutions, x1 and x2, are linearly independent. Okay, now we will be moving on to the next section. Okay, so for the last part of this lesson, we are going to be talking about solutions of non-homogeneous systems. So currently we've already worked with only homogeneous systems when we're given like the initial condition and we're solving for the constants, but that's been without the added function at the end, the f hat of t. So to find the solution of a non-homogeneous system is going to have just kind of like what we've already worked with, complementary and particular parts of it, just like with how we've solved previous differential equations. And how you find the complementary solution is, so we'll write that, how to find complementary solution to eliminate f of t from the system and solve for the associated homogeneous linear system. So basically, we pretty much do what we've done in the past, and we take out the f of t and we plug in our initial conditions just like before. And at least for this section, is our the particular part of our solution is just going to be given to us. So we kind of just add that on to the end. So just to kind of give the form of it, what it'll look like. So it'll be x hat complementary of t plus x hat particular of t equals x of t, our solution. Right over there. So we'll do a quick example of this. This will be example 8. And this is to find the general solution of the non-homogeneous linear system. Okay, so I will give, I hope you can see this, we'll see. I'll give the system here. So these are going, this is our system of equations here. This is x sub 1 prime equals 3x sub 1 minus 2x sub 2 minus 9t plus 13. This is x sub 2 prime equals negative x sub 1 plus 3x sub 2 minus 2x sub 3 plus 7t minus 15. This is x sub 3 prime equals negative x sub 2 plus 3x sub 2 minus 6t plus 7. And setting up our, you could set up your coefficient matrix from here on out, but here's what we're gonna do, I think. Here's what we're gonna do. Actually, we're gonna do pretty much the same process as what we've done before. So your solutions, I'll give the solutions to us. So x sub 1. Okay, so our three solutions that we were given was x sub 1 hat, and our vector matrix is 2e to the power of t, 2e to the power of t, and then e to the power of t. X sub 2 hat is 2e to the power of 2t, 0, negative e to the power of 2t, and then x sub 3 is 2e to the power of 5t, negative 2e to the power of 5t, and then e to the power of 5t. And then our if it's visible, I'll write it down here. Our coefficient, or not our coefficients, our initial conditions are going to be 0, 2, 6. And basically the process from before is what we've kind of been doing like this whole lesson. I'm not going to go over it because we've done it so many times and for the sake of time, but when you plug in your initial conditions for our to find the constants in front of the values, we end up getting the complementary solution. You can go through this, but that might be helpful if you want extra practice in the process of finding what the coefficients are for your general solution. But for the sake of time, I'm just going to write it out. Okay, so our complementary solution looks like this, and it is in the first row we've got 4e to the power of t, negative 6e to the power of 5t, 2, 4e to the power of t, 0, negative 2e to the power of 5t, 2e to the power of t, 3e to the power of 3t, e to the power of 5t, and then our given particular solution, because at this point in time we are just going to be given the particular, is a column vector is 3t, 5, 2t. And then the general form of these solutions, which I will write over with no glare, hopefully. I will write over here. So what we do is we've talked about like adding everything together. So these would just be added on to the end of this. And then we can actually split them up, as we've done earlier in this lesson, into three different solutions. So the first one, x sub 1 of t, is going to be equal to 4e t to the negative 6e to the power of 5t plus 2 plus 3t. See, we just took the 3t from, it's hopefully maybe visible, I don't know. There's 3t is the first vector that is going to be visible, or the first term in our vector, and that's just added onto the end of our solution over here. And then x sub 2 of t is equal to 4e to the power of 2, or to the power of t, minus 2e to the power of 5t plus 5. 5 is the part of our particular solution that we're adding on. And then the last equation, x sub 3 of t, is equal to 2e to the power of t plus 3e to the power of 3t plus e to the power of 5t plus 2t. And basically the principle here is that we're just adding on these last parts. I'll just box them so it's visible. These are the last parts that we're adding on from our particular solution. So we will eventually get to solving that later on in this chapter, but for right now, when the particular solution is given to you, it is just added onto the end of your complementary solution. So that is the end of my lesson for 5.1 matrices and linear systems. I tried to fill in all the gaps. I hope that was enjoyable and clear. Thank you.